In this lecture, we'll see the concept of linearization for nonlinear systems around equilibrium point. So, for this discussion, we'll start uh, on the basis of a one-dimensional system to understand the idea, and then we'll see how it is actually going to look forward as we look in the uh, higher dimensional systems. Okay, so let's say that we have a autonomous system which is of the form x dot equal to fx, and we are looking into a one-dimensional system. And suppose the fx that is under consideration is x minus 3, x minus 5, or to put it, we'll have x square minus 8x plus 15 as the fx with us. Now we know that we can draw the vector field of this. Okay, to ease the way in which vector field can be drawn, let's say this is the real axis, and suppose this is the x-axis, and this is, let's say, the f of x axis with x equal to 0 being here and fx equal to 0 being also at this particular point. So this is the origin of the xfx axis system. Now if you plot fx minus 3, then what happens is the plot is going to pass through 3 and 5. So essentially the plot is going to roughly look like this. Okay, so this is x equal to 3 and this point is x equal to 5. So if you look for the vector field, in such case, we'll only worry about the sense of direction of the vectors along the real axis. Okay, so for all points to the left of 3, we'll have vectors which are essentially pointing towards 3, because fx has positive value for values less than 3, then fx has negative values for values more than 3 but less than 5. So for all points between 3 and 5, we'll have vectors associated such that they are pointing away from 5 but towards 3. And then for the points which are actually onto the right side of 5, ones which are more than 5, you will have vectors which are pointing away from 5. So from this vector field diagram, we can conclude that 3 is a stable equilibrium point, whereas 5 is a unstable equilibrium point. Right. Now, what is the slope that you have for the curve fx with respect to x at the point x equal to 3? Okay. So what is del f by del x? I am basically looking towards the sign of the slope, whether the slope is positive, whether the slope is negative, or whether the slope is 0. So what you see here is at x equal to 3, you have a negative slope associated at x equal to 3. Okay. And similarly, at x equal to 5, you have a positive slope associated with x equal to 5, right? Positive slope. So at x equal to 3, this is negative, and del f by del x at x equal to 5 is positive. And note that x equal to 3 is a stable equilibrium point and x equal to 5 is an unstable equilibrium point. So it looks like that the slope in this case can be related to the stability of the equilibrium point under consideration. So if the slope around the equilibrium point is negative, we can classify the equilibrium point to be stable, and the slope around the equilibrium point, if it is positive, we can classify the equilibrium point as unstable. Okay. So if del f by del x for this one-dimensional system is negative, then the equilibrium point is stable. If del f by del x at the equilibrium point is positive, then the equilibrium point under consideration is unstable. Okay, let us take a look at another example. When fx is sin x, so this is the x-axis. If we just plot fx so that it aids us in plotting the vector field, so let's say this is the sine of x, okay, and it continues. So what are the equilibrium points under consideration? The equilibrium points that we have are these ones. These are the equilibrium points, right? So let's start with the equilibrium point at 0 0, which is this. Now for points towards the left of 0 but to the right of this particular point, how do you think the vectors are going to look like? Sin x is negative, so the vectors are going to point in this direction. For the points towards the right of 0 but to the left of this point, the vectors are going to be pointing away from the origin but towards that point. Similarly, if you keep on doing the getting the sense of the vectors for the vector field, what you get is essentially something of this form, right? So now what you observe is 0 0 is going to be a unstable equilibrium point. This equilibrium point would be stable. This is unstable. This is stable. Similarly, this point here is stable, and this point here is unstable. Okay. Now notice the slopes, basically del f by del x, corresponding to each equilibrium point which you have classified as stable or unstable. You can notice that the slope, for example, at the origin here is positive, but the slope about the next equilibrium point to the right of the origin, which is this one, is negative, and so on. So what you observe is the equilibrium points which are unstable are associated with the positive value of del f by del x, and the equilibrium points which are stable are associated with the negative value of del f by del x. Okay, of course we are evaluating del f by del x at the equilibrium point under consideration. Okay, so del f by del x at x equal to x star, we get positive, implies x star is unstable, where x star is the equilibrium point. Similarly, del f by del x, if we evaluate at x star and we see that it is negative, then x star is a stable equilibrium point. Okay, so if you are given with a one dimensional system, if you calculate the equilibrium points without even plotting the vector field. You just compute del f by del x and evaluate the value at the equilibrium point that you have, and what you essentially will get is a value whose sign will indicate whether the equilibrium point is stable or unstable. Okay, so but now what if the value of del f by del x is 0? We've seen for the cases when the slope is either positive or negative, but we are not. So basically, the slopes are non-zero. The evaluated slopes of f with respect to x. Now, what if the slopes are zero? For example, let's say f of x is x cubed. So in this case, with this as the x-axis and this as the f of x axis, the solution trajectory will sorry, the fx x cube will actually look like this. Okay, so what is the slope? For that we have to see what is the equilibrium point. So the equilibrium point is x equal to 0 is the equilibrium point, and del f by del x evaluated at x equal to 0 is 0. So the slope here is 0, which is also evident from the graph. Now let's come to the sketching of the vector field. So this is essentially the equilibrium point. Now, what would be the sense of the vector direction sense of the vector field? For all points towards the right of 0, the vectors point away from 0, and for all points towards the left of 0, the vectors point away from 0. Right. So essentially, it is indicating that this is a unstable equilibrium point. So possibly, with if we have a zero slope, then it looks like the equilibrium point under consideration can be unstable. But before we draw any conclusion, let us look into another example. When f of x is minus x cube. So in this case, with this as the x-axis and this being f of x, we have f of x versus x to look something roughly like this. The x equal to 0 point is the equilibrium point. What we have is del f by del x evaluated at x equal to 0. The equilibrium point is 0, so the slope of f with respect to x at x equal to 0 is 0. What is the sense of direction as far as the vector fields are concerned? For all points toward the right of 0, you'll have vectors pointing towards the equilibrium point x equal to 0, and for all points toward the left of 0, you'll again have vectors pointing towards the point x equal to 0. So from this rough vector field idea, what we can say is the point x equal to 0 is a stable equilibrium point. Okay, so when del of f with respect to x, or when the slope of f with respect to x at a given equilibrium point is said to be 0, so if you say, let's say that know that the slope is 0, essentially you cannot for sure say just from the information of this slope that whether the equilibrium point under consideration is stable or unstable. Okay, so basically for zero slope it becomes inconclusive, but for positive slope it is unstable, and for the negative slope it is definitely stable. So how does this idea so okay, so how does this idea get carried forward to higher dimensional systems? So what you see here is the slope essentially represents the behavior of the nonlinear system in a very close proximity to the equilibrium point. Okay, so let's say that you have uh, equation, or you have autonomous system of the form x dot equal to f of x belongs to Rn, f maps from Rn to Rn, and x star is the equilibrium point under consideration. Huh? Okay. So if x star is the equilibrium point under consideration, f of x star is definitely going to be 0. Now let's say that any point x is just a perturbation of x star. Any point in the proximity or in the neighborhood of x is a perturbation of x star, where delta x is a small perturbation. Okay, this can be any small perturbation in Rn. So essentially, we are considering some locality around the x star. Okay. Now, what is x dot? X dot is nothing but d by dt of x star plus delta x, which is nothing but the derivative of delta x itself, the perturbation. So essentially, the uh, variation in x is same as the variation in the perturbation itself. Okay. Now we also know that x dot is f of x, which is nothing but f of x star plus x. Now the perturbation is considered to be small enough. Okay. And using Taylor series expansion, I can express it as f of x star plus del f by del x evaluated at x equal to x star. This plus the higher order terms that we have. Now, because del x is small, these higher order terms can be neglected. Okay, which means x dot, which is uh, approx, and of course, this quantity here is 0 as mentioned. F of x star is 0. So f of x, so x dot is approximately del f by del x evaluated at x equal to x star delta x. Okay, and what is x dot? It is basically the change in the perturbation itself. So we can say that the perturbation dynamics del x dot is approximately this. Okay, so this is how things will evolve. Now if you notice, for an autonomous system, this guy here is a constant real matrix of the size n cross n. So essentially what you have is this. Now for stability, what do you need? That the perturbations should die out, which means if delta x eventually goes to 0, then x goes to x star. That is when you will classify um, x star as a stable equilibrium point. Now if delta x dot has to go to 0, then what do you need? You need all eigenvalues of A must have negative real part. Okay, and please notice that this is a linear system. So this is the linearized information about the nonlinear system x dot equal to f of x. The equilibrium point whose stability is being studied for this linear system is the zero equilibrium point, which is 0 n. And the stability information of the zero equilibrium point for this linear system will give information about the equilibrium point x star that we have for the non-linear system. Okay, so all eigenvalues of a must have negative real part. If this is true, then 0 n is a have negative real part, then this should imply that 0 n is a stable equilibrium point for the linear system that is under consideration, that has been obtained after linearization, which means x star is a stable equilibrium point for the non-linear system x dot equal to f of x. If let's say at least one eigenvalue of a has positive real part, if one eigenvalue of a is positive real part, then it means 0 n is an unstable equilibrium point for the linear system. And on top of it, so this will imply that the equilibrium point of the uh, non-linear system, that is x star, about which this linearization was performed, this process is called linearization. So the linearization was performed. This equilibrium point x star is a unstable equilibrium point. Right. So if all eigenvalues of A have negative real part, then the zero equilibrium is a stable equilibrium point for the linear system, which indicates that x star is a stable equilibrium for the non-linear system. Similarly, if A has at least one eigenvalue with the positive real part, then 0 is an unstable equilibrium point for the linear system, and hence x star becomes an unstable equilibrium point for the non-linear system in hand. Okay, now in case of a two-dimensional system, if uh, let's say that the system under consideration is x dot equal to f of x, and the linearized version that we get here is this form. Okay, so this is for the case when x belongs to R2. So it's considering for two-dimensional system. A stable node implies that the equilibrium point under consideration is also a stable node. An unstable node implies that the equilibrium point under consideration for the nonlinear system is an unstable node. A stable focus for the linearized system indicates that the equilibrium point for the nonlinear system is also a stable focus. So these behaviors for the nonlinear system's equilibrium point are essentially local around some small neighborhood, not in the entire state space. Okay. If the equilibrium point 0 is unstable focus, then for the nonlinear system, x star can also be classified as a unstable focus. If it's a saddle point for the linear system, then the equilibrium point x star is a saddle point, will have a saddle point behavior for the nonlinear system. But if we take as a center, if 0 turns out to be a center, which means A has purely imaginary eigenvalues, then we cannot conclude anything about the stability from the linearization. Okay, even in higher dimensional systems, if all the eigenvalues are real for the linearized system and all of them are negative, then you have a stable node. Okay, if all the eigenvalues are real and one of them is positive, then you have a unstable node. Okay, so the corresponding x star or the equilibrium point also becomes a uh, unstable node accordingly. So this is being concluded for x star while this is being concluded for 0. Similarly, if the eigenvalues of A are such that there is at least one eigenvalue whose real part is 0, while the real part of other eigenvalues it is not positive. Okay, so if in the linearized system for A, if you see that one of the at least one of the eigenvalue has 0 real part, while the other eigenvalues real part are not positive, then we cannot draw any conclusion about the stability of the equilibrium point x star in the non-linear system. Okay, so I'll put it down. All eigenvalues are negative, then x star is stable node. All eigenvalues are real with at least one positive eigenvalue, then x star is unstable node. If at least one eigenvalue has 0 real part with remaining eigenvalues not having positive real part, then stability of x star, the equilibrium point of the nonlinear system, from linearization is inconclusive. Okay, this is we are talking of when A is n cross n. We are talking of an n-dimensional uh, system. So, in the next lecture, we'll take up some examples of linearization and we'll see how things can be concluded about the equilibrium point for nonlinear systems. We'll stop here. Thank you.